All right, welcome back. We're going to cover section 2.3 about conditional probability. Now that we've kind of discussed the basic notion of probability back in 2.2, we can talk about conditional probability. And basically, what a conditional probability does is it narrows our attention, it restricts our attention to just a subset of the sample. So instead of computing a probability on the entire sample space, we assume that something happens and then compute the probability of something else happening while operating under the assumption that the first thing occurred, right? So let's get into it. Conditional probability is really useful. Most of the probabilities that we'll be computing when we are performing inference at the end of the semester are going to be conditional probabilities. In particular, p-values, right, are conditional probabilities. So here is the notation for conditional probability. We read this, the probability of E given F. So that line right there is read given, right? And I stress that because I think if you can remember how to read the symbol, it will help you remember what the symbol means, right? This is the probability of E given F. In other words, it's the probability that E occurs if we're given that F occurs, right? It's the probability that E occurs if we know for a fact that F occurs. It's not the probability of E over F. Okay, it is not that. It is the probability of E given F. And it's not computed by dividing probability of E divided by probability of F. There may be cases where that works out, but in general, it is not true that probability of E given F is the probability of E divided by the probability of F. What we have to do when we're trying to compute a conditional probability is just think through the scenario, okay? So let me walk you through a few examples. This first one is going to be about a deck of cards, right? So it says, suppose that you draw a card out of a standard 52 card deck. I'm going to get rid of this little statement so it won't be there in your notes when you're watching this video, but suppose you draw a card out of a standard 52 card deck. Part A asks, what's the probability that you draw a heart? And then it asks, what's the probability that you draw a heart given that the card is red? Okay, so the probability that we draw a heart. There are 13 hearts in the deck and 52 cards in the deck in total. So the probability of drawing a heart is 13 out of 52, which reduces to 1/4, which is 25%. Now, some of you may have realized that that was going to be the answer because 1/4 of the cards in the deck are hearts, and that's totally fine. That's a totally fine way to figure out that probability. But now for the follow-up question, it says, what's the probability that you draw a heart given that the card is red? So this time we want the probability that we draw a heart given that it's red. Let's see how that changes things, right? We're given that the card is red, so we know for a fact that the card is red. So it's as if there are no other cards in the deck. There are only red cards in the deck. Well, out of those red cards, of course, 13 of them are hearts, and then there are 13 more red cards that are diamonds. So in total, there are 26 red cards in the deck, right? The black cards don't matter. So looking at a picture of a deck of cards, right, it's like the red ones are the only ones that count for this particular problem, right? We only care about the red cards. The rest of the cards in the deck don't matter. So there are 26 of these, right? 26 of these cards, and 13 of them are hearts. So it's 13 out of 26. That would be that conditional probability. 13 out of 26 reduces to 1/2, or 0.5. Okay? Because half of the red cards are hearts, right? 1/4 of all the cards are hearts, but half of the red cards are hearts. So that's how conditional probability works. Let's look at another example. Part B says, what's the probability that you draw a 7? So probability we draw a 7. Well, there are 4 sevens in the deck, so we would say it's 4 out of 52, which reduces to 1/13. As a decimal, that would be approximately 0.0769. Oh, and I circled the wrong one, right? I want to circle the reduced fraction as my final answer. So 1/13. Now the next question, what's the probability that you draw a 7 given that the card is a heart? So probability we draw a 7 given that the card is a heart. Well, let's see. Let's go back over to our deck of cards. Let me erase all of this nonsense that I just did. But this time we're given that the card is a heart. So we're going to restrict our attention to just the hearts in the deck. And it's as if the rest of the cards in the deck don't exist. Okay, so we ignore all the rest of the cards, just focusing on these guys right here. Then the question is, what's the probability we draw a 7? And the answer would be, well, there's only one 7 of hearts, right? So it would be 1 out of 13. Okay, so 1 out of 13. One out of 13. Notice that this time, the condition didn't change the probability, right? In part A, when we looked at probability of H, we got 1/4, but when we looked at probability of H given R, we got 1/2. Whereas in part B, when we computed probability of 7, we got 1/13, and when we computed probability of 7 given H, we also got 1/13. So sometimes that conditional doesn't really change the probability, right? But sometimes it does. Let's look at one more example. This one's kind of a weird one, but let's think through it. It says, what's the probability that you draw a 7? Well, we've already done this, right? Probability we draw a 7 is 4 out of 52, which reduces to 1/13, which is approximately 0.0769. But now the next question is, what's the probability that you draw a 7, or at least it should say 7. What's the probability that you draw a 7 given that the card is a king? Okay, so probability that we draw a 7 given that the card is a king. Well, if you know that the card is a king, then you know that it isn't a 7, right? Again, we can look at the deck of cards to convince ourselves that that's the case. But kings and 7s are both ranks, right? So if you know that the rank of your card is a king, right? If you know that you're one of these cards, you're given that the card is a king, well, then it can't be a 7, right? Because you know for a fact that it's a king. So the probability that you draw a 7, given that you drew a king, is 0 out of 4, right? You were given that you drew a king, so there are 4 possibilities for the card that you drew. But none of those 4 cards is a 7, so it would just be 0. So this time, right, again, the conditional changed the probability. So that's what conditional probabilities, that's how they work, right? They restrict our attention to just a subset of the sample, and this is the restriction. This is what we restrict our attention to, right, in each case. We restrict our attention to what we're given. We're given, in this case, that the card was red, so we only looked at the red cards. Here we were given that the card was a heart, so we only looked at the hearts. And here we were given that the card was a king, so we only looked at the kings. And out of all the kings, well, obviously none of them were 7s, right? Let me give you another set of examples. So this set of examples uses a contingency table, which we will define in more detail in a second. But this contingency table is supposed to represent the number of extracurricular activities a random sample of teenagers does in a given week. An individual from this study is chosen at random. Let's let A be the event that the individual is male, and let's let B be the event that the individual does 3 activities. Now, part A asks us to compute the probability of A, right? A is the event that the individual is male. It looks like in our study there were 200 males out of 400 individuals. So probability that the individual was male is 200 out of 400, which reduces to 1/2. Part B asks us to compute the probability of B. B is the event that the individual did 3 activities. So it looks like in our study there were 111 individuals who did 3 activities, right, out of 400 individuals in the study. So probability of B is 111 out of 400. And that does not reduce, but we can see what it is as a fraction. It's approximately 0.2775. Actually, it's exactly equal to 0.2775. Okay. Now part C asks us to compute the probability of A given B. A is the event that the individual is male, okay? And B is the event that the individual did 3 activities. So we want to know the probability that the individual is male given that the individual did 3 activities. So we're given that the individual did 3 activities, which means we're only going to look at these individuals, right? We're going to restrict our attention to the individuals who did 3 activities. It's like the rest of the people don't matter. They're not even part of the study anymore. And then we're going to ask ourselves, out of these people, what's the probability that the individual was male? Okay? And it looks like out of those people, 40 of them were male out of 111 people in total. So it would be 40 out of 111. Okay, which doesn't reduce, but 40 out of 111 is approximately 0.3604. So probability of A was 50%, but probability of A given B was only about 36%. Okay, so the probability that a randomly chosen individual from this study is male is 50%, but the probability that an individual is male, given that they participated in 3 extracurricular activities, is just 36%. Okay, and then part D asks us for probability of B given A. This would be the probability that an individual participated in 3 activities, given that the individual was male. You might think, well, didn't we just compute that here? But we didn't, right? In the case of part C, we were looking at the probability that if the individual did 3 activities, what's the probability they're male? Whereas in part D, we're looking at the probability that if the individual's male, what's the probability they did 3 activities? And to show that those aren't the same thing, let's go ahead and compute this, right? So if we're given that the individual is male, let me erase my scribbles. Okay, we're given that the individual is male. That means we're going to restrict our attention to just these individuals. And it's like nobody else in the study matters. Okay, we're only going to look at these ones. And now we want to know, out of these individuals, what's the probability that the individual participated in 3 activities? And that would be 40. Okay, there were 40 of those out of 200. Okay, 40 out of 200. And that does reduce. Let's see. So 4 out of 20, so 1/5. So this would be 20%. Okay. So again, what a conditional does is it just restricts our attention to a subset of the population. And in our case, in this last example, we were restricting our attention to the men in the study, whereas in part C, we were restricting our attention to the people who had done 3 activities, right? Okay. So I'll let you kind of read through this summary on your own. But basically, yeah, what probability of E given F does is it changes our sample space from the entire sample space S to just F, right? We restrict our attention to just F. Let's practice a little bit more with these contingency tables. So a contingency table shows the frequencies of 2 variables by arranging the possible responses of one variable in rows and the possible responses of the other variable in columns. For example, a group of children were asked what their favorite Pokemon character was, right? So we've got those in columns. And then they were also asked whether they prefer grapes or raisins, and so that's given in rows, right, in the top row. And so this table here is a contingency table, right? It tells us how many children fall into each subcategory. With data arranged into contingency tables, we can make all kinds of observations, right? And it's especially useful if we have if we compute the probabilities, if we compute the proportions involved here, right? So, for example, we can see that kids who like Bulbasaur are equally likely to prefer grapes and raisins, right? Because there were 2 kids who liked Bulbasaur, one of them liked grapes and the other one liked raisins. We have a pretty small sample size here, of course, so it's hard to make really firm predictions, but that's what the data would indicate. The data that we have at our disposal would indicate that, right? Anyway, so we will be using contingency tables quite a bit later on in the semester. For now, let's just practice computing some probabilities using contingency tables, like the one that we just did previously. So number 3 here says, suppose a study of speeding violations and drivers who use cell phones produced the following data. So in this column, it looks like the variable is whether or not the individual uses a cell phone while driving, which you shouldn't do, right? And then along the top row, it looks like the variable is whether or not you got you had a speeding violation. So like you got a ticket or something. Okay. So part A says compute the probability that a driver is a cell phone user. Well, it looks like there were the cell phone users are in this row, right? It looks like there were 305 of them out of 755 people total in the study. So it would be 305 out of 755. And that definitely reduces. So that reduces to 61 out of 151. As a decimal, it would be about 0.4040. Okay, part B says compute the probability that a driver had no violation last year. No speeding violation. That would be these individuals. These are the ones who had no speeding violation. It looks like in total there were 685 of them, right, out of 755 people in the study. So it would be 685 out of 755. Which comes out to, that's the same as 137 out of 151, which is approximately 0.9073. So almost 91% of people did not get a speeding violation last year, which I think is probably true, right? That jives with my kind of common sense. Okay. Part C says, compute the probability that the driver had no violation last year, given that the driver is a cell phone user. Ooh, okay, so now we have a conditional, right? We're given that the driver is a cell phone user. So we're going to restrict our attention to these individuals. And this time it's like the rest of the individuals in the study don't matter. We only care about the people who use their cell phones while driving for the purposes of Part C. And we want to know, out of these people, what's the probability that the driver is a cell phone user? Or I'm sorry, we want to, out of these people, we want to know what's the probability that the driver had no speeding violation. That would be these people, right? 280 of them had no speeding violation. So 280 out of 305. Okay. That's 56 out of 61, which is approximately 0.918. Okay, one more. Let me erase my scribbles. Okay. It says, compute the probability that the driver had no violation last year, given that the driver is not a cell phone user. Okay, so that would be these individuals. Okay, and the question is, out of these individuals, what's the probability that the driver is not, or sorry, what's the probability that the driver had no violation? That would be these ones, 405. There are 405 of them out of 450. So 405 out of 450. That reduces all the way down to 9/10. It's exactly equal to 0.9. So 90% of them. Okay, so then part E asks us kind of a follow-up question. It says, based on your calculations, would you say that using your cell phone while driving affects whether or not you will have a speeding violation? And this is sort of unexpected to me because, okay, when we computed the probability that you got a speeding violation, assuming that you were a cell phone user, we got a larger probability than we did when you assume that the driver is not a cell phone user. So, in other words, what I would have thought was that if you're using your cell phone while driving, you're going to be more likely to have a violation. But it looks like the opposite is true. It looks like if you are not a cell phone user, then you're going to be less likely to not have had a speeding violation. In other words, you're more likely to have had a speeding violation if you are a cell phone user. So that's kind of unexpected, but the difference is not substantial, right? I mean, these numbers are really pretty close to each other. But we would say it actually appears that people who don't use their cell phones while driving are slightly more likely to have a speeding violation. Which is very strange, but that's what the data indicate. Again, it's not substantial, right? It's a slight difference, but it's probably not statistically significant. that's something that we will talk about in the next unit. Okay, one more set of examples. So number 4 here says, a survey was conducted by the Gallup organization in which 1,017 adult Americans were asked, which of the following statements comes closest to your belief about God? You believe in God? You don't believe in God, but you do believe in a universal spirit or higher power? Or you don't believe in either? The results of the survey by region of the country are given in this contingency table here. Okay. And part A asks, what's the probability that a randomly selected adult American believes in God? Well, it looks like in total there were 787 adult Americans who believed in God out of the sample of 1,017 adult Americans. So we would say, all right, probability you believe in God is 787 out of 1017. So that's about 77%, right? 0.773. Oh, sorry, 0.7738 approximately. Okay, part B. What's the probability that a randomly selected adult American lives in the East? Okay. Well, in total, right, there were 255 Americans in this survey who lived in the East, okay, out of 1,017. So we say probability you live in the East is 255 out of 1017. Okay, so that's about 0.2507. Okay. Part C. What's the probability that a randomly selected adult American who lives in the East believes in God? Okay, so now we know that the American lives in the East, right? It says, what's the probability an adult who lives in the East, right? Who lives in the East believes in God. So we're restricting our attention now just to the people who live in the East. In math symbols, we would write this as the probability of something happening given that the person lives in the East, right? We want to know what's the probability person who lives in the East believes in God. So this would be the probability of G given E. It looks like there were 204 believers out of 255 people from the East. So 204 out of 255. That comes out to exactly 80%. Oh, which means this thing must reduce, right? This reduces to 4/5, which is 80%. Okay, part D. What's the probability that a randomly selected adult American who lives in the West believes in God? Who lives in the West? Okay, so this time we're going to just look at people who live in the West. So that's these people. That looks like it would be 152 out of 254. So probability you believe in God, given that you live in the West, is, what did we say? 152 out of 254. Okay, that reduces to 76 out of 127, or as a fraction it would be about 0.5984. Part E, based on your calculations, do you think that the likelihood that a person believes in God is affected by where in the country they live? And I would say yes. Like here, there seems to be a more substantial difference. Like if you live in the East, you're more likely to believe in God than if you live in the West. Yes, it seems that if you live in the East, you're more likely to believe in God than if you live in the West. Okay. Now, part F is asking, what's the probability that a randomly selected adult American who believes in God lives in the East? So, randomly selected adult American who believes in God. We're given that they believe in God. And we want to know what's the probability that they live in the East. Okay. All right, so we're given that they believe in God. So this time, we're going to restrict our attention to those people who believe in God. And we want to know, out of these people, out of this column, what's the probability the individual lives in the East? It looks like that would be 204 out of 787. Okay, and that comes out to about 0.2592. If I haven't stressed this enough yet, let me just say, clearly, in this case, probability of G given E is not the same thing as probability of E given G. And in general, it's just not true that probability of E given F is equal to probability of F given E, right? These are different concepts. But that's it for conditional probability. I think that'll just about cover what we need to know for conditional probability for now. So we'll stop there, and I will check in with you in the next section.